was shown that they show some kind of critical behavior B naught chi to the power phi, where phi is related to nu parallel and nu perpendicular. The nu parallel, nu perpendicular actually is related to the temperature dependence of the correlation function, xi parallel and xi perpendicular. Okay? And in fact, there was some kind of controversy which probably after Lubensky wrote a big paper on this, that which class is belong to this transition, okay? Which anisotropic class is, I mean, is it isotropic or anisotropic? Anyway, so then we found that this particular liquid crystal case, the critical exponent phi is about 0.38. These people have measured long ago. So we find that the similarity of the critical exponent, from this we can actually imagine what is happening. So we realize that these two particles, when they are approaching the smectic-A phase, you have confining plates like this, and now two particles are confining. That means smectic between the two particles is getting compressed. But you know, this layer compression modulus shows this kind of critical behavior. Therefore, the interparticle separation increase with the similar critical exponent tells us that the smectic layers are actually getting compressed in the smectic-A phase. Yeah.
Critical phenomena, I thought is typically for a second order.
This is that's why I am repeating. It is a very, very weakly fast order phase transition. It is really so, really weak, really weak.
When you say weak first order transition, you mean incipient first order transition that's almost like a second order transition?
This is almost like a second order phase transition.
And towards the last part becomes first order.
In fact, see, this is again, there are some experiments, which actually reveals or sort of predict that it is a weakly first order. Some in the beginning actually they thought it is a second order. In fact, if I remember, the theory predicts that nematic to smectic-A would be a second order phase transition. But when the experiment shows no, it is actually weakly first order. It is not really second order.
This for specific measurement.
For specific measurement also. Then there are some lot of actually discussion about that, and still that's why it is believed that it is one of the complex phase transition in short matter. So now
Simulation work in the smectic phase.
no, in fact. Smectic is difficult. I think I know 3 experts smectic in the world is probably the Camion, Randy Camion in Pennsylvania, Joshua Hattewalle, who is also a very good, and probably Tom Lubensky. So they are the person actually who can, in fact, one of our recent results on smectic-C, I am discussing with Professor Tom Lubensky for his, because he had some prediction long ago, seems to be connected to this. Anyway, so now this, as I said, these particles, they have a, how much time I have?
5 minutes.
5 minutes, okay. Sorry, so I think I'll just quickly, can I take 5 more minutes, 10 minutes? Okay, sorry. Okay, so I'll go quick now. These particles, as I said, they have a long range attractive interaction. We can actually guide them to have a self-assembled structure. And for example, we can see I use a laser beam and to make a 2-dimensional colloidal crystals.
So that bubble is the laser beam?
Laser beam, yes, the bubble is the laser beam, okay.
Is it actually forming a bubble there?
Actually what happened, this locally, the nematic order is destroyed. You make a isotropic region, okay. And so you basically create elastic distortion, and overall the system wants to minimize elastic distortion energy. Therefore, any particle around, they will be attracted towards this. Yeah. So, in fact, it was first showed that there are two forces between, the delicate balance between these two forces creates this kind of self-assembled structure. And this is what we did. We found in the nematic phase. So what we actually did that we now decrease the temperature and went to the smectic phase. Okay.
So how big is the ball here?
This is around 5.2 micron. 5.2 micron. Yeah, around 5 micron. Okay. So this is in the nematic phase. We can actually here, I don't know how many, 64? I don't know how many. Oh, but you can make it really big. You can really make a maybe 100 micron into. Already it is 5. How many is there? 1, 2, 3, 4, 5. 6. Yes, around 64 are there. So actually you can.
Is this only in the solution or it
Yes.
is outside also?
No, it is in the nematic liquid crystal.
But you cannot dry it out.
One thing you can do, you can use some photoreactive monomer and then you shine UV light, freeze them and take out. It's possible.
You are talking about whether the colloids can be arranged like this? Oh.
This colloid in the isotropic phase, no. The forces are very different here.
No, I'm talking of these colloidal balls.
Yes.
Large pattern crystal.
Yes. This you can make a solid and take out from the liquid crystals.
Okay, that is exactly
Right. It's possible. So now what we did is that we actually, I show you two video. So we decrease the temperature, okay. And if you look that we have a structural transition from oblique to hexagonal. So I am decreasing the temperature, right. So this transition is driven by the discontinuity in the elastic constant from one phase to other. And this is reversible because you can clearly see when we increase the temperature again, it goes back. So this is a reversible transition, and you have a lattice from oblique to hexagonal structure, okay. And so we, of course, we did this lattice parameter measurement, and I will not go into details. So I have explained the one kind of defect, which is this basically the dipole defect. But as I said, I have different types of defects. Like I can have a Saturn-ring defect. Also, I can make a two-dimensional colloidal crystals, and look at these phase transitions. So this phase transition in the two-dimensional colloidal crystal is actually driven by the phase transition of the medium liquid crystals. Okay. So in this case, the colloidal structure actually irreversibly it breaks down. Okay. If you see that now I am just decreasing the temperature, going from nematic to smectic, you will see that the 2D colloidal crystals break irreversibly because they have these quadruples, they have a smaller binding energy, and when they go to from one phase to other, they have some kind of focal conic line between two colloids in the horizontal direction. That's how they are separated, and they can, since they are so far, they do not come back. This is irreversible transitions. Okay. Now I will not go I think in detail because time is short. So another thing which I want to tell you is that if you have a particle which is having boojum defect, two surface defect, again across transition if you see that the two boojums actually transform into a smectic focal lines. Okay, the both sides. So yes. Now from this analysis of the red plate, we can find out how the smectic layers actually are oriented along these spherical particles. So I think since time is short, I will not go into detail. Then the interparticle separation, what we measured, then we found that the interparticle separation decreases in the nematic phase. Compared to the previous case, it was increasing, but now it is decreasing in this with this defect, and we have sort of understanding from the simulation why actually such decrease is possible. I think I will. Okay, I will show you that you can also make, since the time is short, I am just showing one or two slides. This is a 2D colloidal crystals, and these crystals are made using dimers. The dimers are actually bound by a kind of defect which is non-singular defect. Means that core of the defect is not singular, the order is not 0. Okay, and such 2D colloidal crystals, if you decrease the temperature across the phase transitions, you see this what happens, and this is if you apply electric field. That is with temperature, this is electric field. So you can change the lattice parameter of these 2D colloidal crystals. Okay, and therefore tunable crystal you can actually make. Of course, it's 2D, but 3D making is difficult under microscope. At least this kind of situation. Now I will not go into detail. So I think. He was asking me about this, how do we measure interaction potential? See, so how do I measure the interaction potential? Basically video tracking. We assume that there is no acceleration when two particles approach each other. Therefore, this drag force can be written by this. So dr dt is the velocity, relative velocity, which we can measure. And if we know this, if it is a quadrupolar interaction, so drag force is balanced by the elastic forces. Okay, and this coefficient xi, parallel perpendicular, we can find out from the Boundian motion. Because diffusion coefficient you can find out d parallel perpendicular. D parallel is the parallel to the director, and perpendicular is the perpendicular to the director, that is the molecular alignment. And from this, if you know the drag force, we integrate the drag force, we can get this potential. So this is a platelet type particle. I have not gone into the details, but let me show one maybe slide or last slide or so. So this platelet type particle shows some interesting electrokinetics. This is in one liquid crystal where this liquid crystal do not reorient, but this particle starts moving. Okay. In fact, this is one way of making the active particles or active colloids. Of course, it's driven by external energy. And so we studied this, what kind of defects this platelet type particle forms, and how the velocity depends on the electric field, and basically they show sort of quadratic dependence. Why do they show quadratic dependence? So there are some explanation, and I think I will. So my time is over, right? Okay. So I think I will not go into detail. And also it can actually spin around. They can also spin, okay, around this one. So you can make actually a micro motor by applying electric field.
There is a AC electric.
AC electric field.
Yes,
This is not a normal electrophoresis we know. This is a nonlinear electrophoresis in liquid crystal. The topological defects induced with each particle plays a crucial role in determining their motion. So the difference with the normal electrophoresis or dielectrophoresis with this kind of electrophoresis in liquid crystal is that topological defects breaks the symmetry of this ion flow around the particle. Yes. No, they are. Each particle has a topological defect. No coupling around each other. You can see some of them are rotating clockwise, some of them anti-clockwise. So there is no coupling. Okay. So okay.
If you make the density higher, at some point they will couple, presumably.
Yes, if you, of course, they will interact actually. They will interact and form a self-assembled structure. That's what I have shown that you can actually make this is a platelet type particle, thickness is 200 nanometer. So very thin actually. And you can actually self-assemble them, make a 2D seat, like a seat. Huh? This torque we have not measured, angular frequency we have measured. Oh, this is one thing which we have not understood. We believe that, see, somehow this particle is close to the bottom surface. And though I have applied electric field perpendicular to this substrate, it seems there is a local flow which is parallel to this substrate. One of the possibilities is that these particles gives a planar degenerate anchoring. These liquid crystal molecules are planar degenerate. And ionic flow in the liquid crystal molecule is always higher than this perpendicular direction. Therefore, the flow of ions bottom surface where these molecules are parallel is easier than the other direction. So we believe that there is some local flow, but again, this is not really theoretically understood, but we believe that this is a local flow. It comes because of the planar degenerate anchoring of these molecules, and the particle is close to bottom surface. Okay. See, essentially this kind of motion means that somehow you have broken the symmetry of the ion flow around the particle. Now, the question is, in normal electrophoresis, that symmetry is broken by particle shapes, or you have a charge with the particle. Liquid crystal case, the topological defects break that symmetry. Okay. And okay, I think I will stop and fine. Okay, this is something to do with these droplets, liquid crystal droplets. Actually, you can make them a micro resonator, and in fact, what we showed is that if you have liquid crystal droplets, smectic droplets, where layers are wrapping like this, we put some dye molecules and inject light so that dye gives fluorescence. But now this refractive impedance of the droplet is higher than this outside medium. Outside medium could be water or could be PDMS. Then light is injected, right? They rotate, they circulate inside, and you get a what is called whispering gallery mode optical resonance. And one interesting thing is that this resonance actually you can exploit for detecting some phase transitions which are really weak, like nematic to smectic is second order, almost second order or weakly first order transition. You can see this when you have a slight reorganizational change of these molecules, smectic to nematic, there is a drastic fall in the quality factor. Okay, quality factor is this delta lambda by delta lambda. Okay, so you have a substantial jump. So we believe that even in solid, if you have a material where you have phase transitions, which is really a weak transition, but minute change can give rise to a large physical which is observable quantity like this, and you can detect the phase transition. Okay, so I think I have discussed only the first part of my talk, and as my time is over, and thank you. So if you have any questions, and please, we will be happy to discuss.
Questions?
Can you go back to the slide where you introduced the defects?
Where?
Introduce the defects.
Defect, okay. It is in the first slide somewhere. Maybe I should go this. Somewhere in this. Here. Yeah. Yes.
So there are two images which are taken in microscope.
This image is between a microscope, but between two cross polarizers. Right side, you remove the polarizer.
So how do you remove the polarizer?
Oh, in microscope, we have a slot to just take it out. In microscope, when the light comes, you have two slots, right? Bottom slot and top slot. So you just remove the microscope. Actually, it's a sliding. It's very simple.
Polarizer is an element.
Yeah, because you have a polarizer is basically a kind of Polaroid sheet, right? So, no. This is basically we know normal microscope, right? Now you, instead of using normal light, you use polarized light. That's it. And put another polarizer for that, which we call analyzer, to see the light. Yeah.
So, what is insist that when you make the liquid crystal, unidirectional order it is, why not this translation? So
No, there.
Statistical mechanics, if you do an experiment with needle, if you increase density more and more, at the time after density it becomes orientational order.
Yes.
It's called a nematic phase.
Yes.
So, I am asking you the basic, why it is not translation order?
You can isort that not only nematic, you can also have a positional order, right? I sort that